An operational amplifier by its nature is a difference amplifier. What I mean by that, it actually has a non-inverting and an inverting input, and what it does, it tries to amplify the difference between them. So in reality, if we have just a negative plus in here, so what we have is we have a Vn and we have a Vp in here. So the V out that we get in here is simply some sort of amplified version of Vp minus Vn. That's by its nature, that's what an operational amplifier. But we have seen that whenever this goes to infinity, the difference between these two becomes 0, so Vp minus V is equal to Vn. So without this feedback loop, a negative feedback loop that we have been using, that particular amplifier won't be as useful because what it's trying to do is just amplify as 0. So in this video, what I want to show you is a configuration that will does exactly that, which is take the difference between two different signals, and that will be V1 and V2. And in this particular case, V1 is connected to the inverting input, and V2 is connected to the non-inverting input, and V output should be basically some sort of a weighted difference between V1 and V2. So I will see, I believe, some sort of a V output will be something V2 minus V1 with some sort of a gain in here and a gain in here. So let's try to figure out what exactly these values are by analyzing the circuit. So of course we can analyze the circuit by putting our assumptions in here. For example, we can say that IN is 0, and we can say that IP is 0. And this one here is simply Vp, and this one here is Vn, and of course Vp is simply equal to Vn, and we can write nodal equations at different points within this circuit. But for the sake of just showing a different solution, what I will do in this case is I'll just analyzing using superposition. So I'll take the effective V1 and I'll take the effective V2 on V output, and I'll just basically compute them separately. So let me just do that in here. So I'll take these and I'll just redraw that circuit. And first of all, I'm going to take the effective V1. So to study the effective V1, I'll just turn off V2. And the way I will do it is I'll just basically say, let's remove this here. Okay, we remove that V2 in here, and what do we replace it with? We simply replace it with a wire, okay? And of course we can think about here the 3 and the 4. There will be basically in parallel because they share this node and both of them are connected to ground. So I can replace both of them with one resistor, and that resistor would look something like this in here. It doesn't matter the actual effective 3 and 4, but it will end up with this circuit would look something like this, connected to ground. And since the current that is going inside is actually just simply 0, so we can just simply say, well, that is just simply connected to ground, and that's it. So Vp in this particular case is 0, that means Vn is also 0. Okay, so now, well, we have seen this configuration before. So this is not V0, this is V0 prime because it's effective V1 alone. So V0 prime is just simply, this is an inverting configuration. So that's simply negative R2 divided by R1 times V1. And that's the effect of V0. All right, let's do the same type of analysis for the effective V2. So here's that circuit, the original circuit again. But this case, what I will do is I'll just turn off the V1 source, okay? And of course, if we turn off the V1 source, what we're effectively doing is we're connecting this to ground, and everything else stays the same. So this particular configuration is, I believe, the non-inverting configuration because we have R2 and R1. R2 is fed back to the negative, and then they're connected to ground. But what is it amplifying? Well, it's probably just amplifying the voltage in here, and that voltage in here will be able to compute it. So let me just do that in here. So what we're interested now is V0 prime prime. That's what we're interested in. And since this is just specifically V0 prime prime is just 1 plus R2 divided by R1. And let me just call this here maybe, this is actually Vp, and we're just going to call it V prime prime. That's what it does amplify, because this one here, Vn prime prime, is simply just the same as V prime prime. That's what it does. Okay, so now our task is to figure out what Vp prime prime is. And if you think about it, since there's no current in here, that means R3 and R4 are in parallel, or are in series, sorry. And I know the source voltage across them, which is V2. So V2 gets divided between the R3 and the R4. And what we're interested in is Vp prime prime between that and the 0. So what we're interested in is the voltage across the 4. So let me just do that here. So Vp prime prime is simply V2 times R4 divided by R3 plus R4. So we'll combine these two together, and I'll get that V0 prime prime is just simply 1 plus R2 divided by R1, that's from the non-inverting configuration, times from the voltage division R4 divided by R3 plus R4, and that's times V2. All right, so now we know, just so that we can see it. So the original circuit is that. I know the effective V1. Let me just move it in here so we get to see it. Okay, so I went ahead and I wrote all of these, and basically I have the V0, basically the effective V1 alone, and that's just simply an inverting configuration, and the effective V2 alone, that's simply non-inverting configuration applied to some sort of voltage division. So now if I'm interested in just the V output, that will be V0 prime plus V0 prime prime, and that's simply V0 is simply negative R2 divided by R1, V1 plus 1 plus R2 divided by R1 times R4 divided by R3 plus R4, and that's V2. And if you think about it in here, so this here is a difference amplifier. What it does, it takes V2 is technically connected to the non-inverting, so V2 appeared, everything is in the positive, and the V1 appears to be in the inverting, and that's what we see here is the negative. And if for some reason what we're interested in is some sort of a V out as the same gain for V1 and V2, basically what I'm really interested in, I want V2 and V1 to be exactly amplified with the same exact ratio. So what I'm interested in is this and that to be exactly equal. That's what I'm looking at, with some sort of a gain that is shared between them. I can definitely do that, and that's not very difficult. What we need to do is we need to make sure that this and those are equal, because this will have the same one in here and the same one in here, and they will both be equal to G. So all you have to do is just set the V2 amplification 1 plus R2 divided by R1 times R4 divided by R3 plus R4 to be exactly equal to R2 divided by R1, because the negative goes with the V1 in here, so keep it. So that becomes R2 divided by R1, and now we do a little bit of algebra, and you can spend the time on it, and what you'll end up with is the following. You'll end up with the following, which is R1 divided by R2 should be equal to R3 divided by R4. So if I zoom out a little bit, what I'm asking you to do is to make sure that if the ratios between these two in here is the same as the ratio between these two in here, what you will end up with is an equation that looks something like that, which is V0 equals, and you can substitute, for example, everything instead of R3 and R4, I'll just basically substitute it. You'll end up with the following, R2 divided by R1, and that's V2 minus V1. That's what you will do. So just substitute these in here, and that's what you'll end up with. So V2 and V1 are basically, we took the difference, and the gain between them is R2 divided by R1, and that's about it. And it's the same exact gain. All right, so let's take this equation and just use it in a useful circuit. So in here, what I have done is I have done the following. I have provided you with the following difference amplifier, and in this particular difference amplifier, what I provided is the input is 15 and the other input is also 15, and I have decided that this should be 100 kilo ohms and this should be 50 kilo ohms. And what I have done in here, instead of providing 100 kilo ohms, I provided 101 kilo ohms, and this is here is 50 kilo ohm. So technically this equation does not apply anymore because the ratios between them is not exact now. And this is actually some error, like for some reason or another, the resistor, maybe you got 100 kilo ohm resistor and that was supposed to be 100 kilo ohm resistor, but because of manufacturing errors it became 101. So let's see the effect of like this mismatch between the ratios between the different resistors. So that means that instead of using that nicer equation, what we need to do is we need to use the bigger equation, which is the one right here, okay? And that will give me the value between V1 and V2. All right, so let me just write that here. And that will be here, okay? So let's figure out what the values of R2 and R1. I believe this is R2, this is R1, and I think this one is, let me just double check. This one is R4, and this one here is R3. Let me just double check. R2, R1, R3, R4. Yes. Okay, so let's figure out what these values are. So R1 happened to be 50 kilo ohms, R2 happened to be 100 kilo ohms, and then R3 happened to be 50 kilo ohms, and R4 happened to be 101 kilo ohms. This is basically the mismatch in here. So let's substitute all these values, and I know that V1 equals V2 equals 15 volts. So if they were exactly matched, I should get an output that is exactly 0. but they are not matching. So let's double check how far off from 0 I am. So that will be basically negative R2, which is 100 divided by R1, which is 50 kilo ohm times V1, which is just simply 15. Okay, plus 1 plus R2, which is 100 divided by 50 times R4, which is 101 divided by R3, which is 50 plus 101, and that here is 15. And the answer is, the answer for V0, instead of being 0, it will be 0.099 volts, which is simply or close to 99.34 millivolts. While it is very small, so this 1 kilo ohm mismatch between this R4 and R2 have generated something that is about 100 millivolts. It might be very, very close to 0. However, if these signals originally were not 15 volts, for example, and it was something a little bit different, for example, bias signals similar to hard signals. Hard signals is actually less than that, so that particular difference amplifiers might not be the best for very small signals. It might work, but not in all cases. Anyhow, just to summarize, what I have shown you in here is some sort of a configuration that will give me the difference between two signals, V1 and V2, with specific amplification based on the values of R2, R1, R4, and R3.